Today on What Are They Doing? Josh does more math, Robert builds a doomsday device, John does editing, and Mike says more words. More words. For MET 213, we were tasked with creating a dynamics demonstration. We originally thought about dropping an egg,
We should have dropped an egg.
but the clear choice was building a gigantic cannon made from a car's coil spring. Once we had the coil spring, everything magically fell into place. After a short safety briefing, it was time for testing. The cannon works by compressing the spring a certain distance using a rod that passes through the spring, which is connected to a quick release, and a winch that pulls the spring down. The barrel is then pivoted at an angle.
This is problem 3-28 from Dynamics Spring 2017. So the first thing that we did was solve for the initial velocity. We got a K of about 132. This K to solve for the initial velocity. The initial velocity, we use the principle of energy. Initial velocity is equal to the square root of spring constant times deflection squared minus 2 sine of theta, mass of projectile times gravity times coefficient of static friction times the distance, all divided by the total mass. And that gives us the initial velocity. Now, when we first did this, we did not account for the mass of the bolt that was pulling our spring down, so we were getting our numbers way off. Once we accounted for the mass of the bolt as well as the mass of the projectile, our numbers were spot on. The velocity final at y, at the top of its path, there's its path, start point, finish point. So the velocity at the top point is going to be 0. So we can neglect that. Final y is initial velocity times the sine of theta squared divided by twice gravity plus the initial y position. Once you have this here, you can solve for the final y position at the top of the path when velocity is 0. Once you have that, you can solve for the time that it takes to reach the top of the path.
We should have dropped an egg.
I put all this into one big equation, and I came up with the distance, delta x, equals velocity initial in the x divided by gravity times velocity initial in the y plus the square root of velocity initial y squared plus twice gravity initial y position. And I use this formula to calculate the distance that it'll go. So after we tested a few times, we realized that we were still we were still overestimating how far it went. So I decided that I would want to calculate for wind resistance, and here's
We're done here. Turn it off. Turn it off. No, stop it. You're done. You're done.
all right, and that is how you solve for wind resistance right there. All right, and that is how we did it. And our results, we had 3 different results.